Next, we go for space complexity. Space complexity of an algorithm is the amount of computer memory is required to run the completion of an algorithm is called as space complexity. So space complexity of an algorithm is the sum of two components. First one is fixed part and second one is variable part. Fixed part is the independent of input and output characteristics. So for example, space needed for input and output variables. Typically it includes the space needed for the code, space needed for the variables, space needed for the constant. How much space required for the variables, how much space required for the constant, how much space required for the code of the algorithm. So these sum indicates the fixed part. Next, second part is variable part. So the space needed by the variable part consists of space needed by the component variables whose size is dependent on the particular problem instance at runtime. So here this variable part only considered if the algorithm consists of for loop, while loop, do while loop, switch case. So at that time we are considering only variable part, otherwise the variable part is equal to 0. So then space complexity of an algorithm P is indicated by S of P is equal to fixed part plus variable part. Fixed part is C and variable part is S suffix P. Okay. So here space complexity of an algorithm is the amount of computer memory required by an algorithm to run to completion of an algorithm. So next, space needed by an algorithm is the sum of two components. So one is fixed part and second one is variable part. So here fixed part is independent of input and output characteristics. Fixed part typically typically includes space for code, space needed for variables, space needed for variables, space needed for constants, space needed for constants. Next, variable part the space needed by a variable part is the space needed by the component variables, space needed by the component variables whose size is dependent on the particular problem instance. Instance at runtime. It typically includes space needed for register stack, reference variable, register stack space needed for reference variables. So therefore, S of P is equal to C plus S suffix P. So here C is fixed part, S suffix means variable part. So here where P is an algorithm, S of P is the space complexity of algorithm P. So space complexity mainly concentrate on S suffix P. Okay. So S of P is equal to C plus S suffix P, where C is called the fixed part. So here fixed part is independent of input and output characteristics. So fixed part typically includes the space needed for the code, space needed for the variables, and space needed for the constant. So the total sum is called as the fixed part. So this part is indicated by letter C. Next, variable part. So variable part, the space needed by the variable part typically consists of space needed by the component variables whose size is dependent on the particular problem instance at runtime. So here we are mainly concentrate on variable part. So this variable part typically includes the space needed for the reference variables and space needed for the register stack space. Okay. So here S suffix P is nothing but, so space, this is a variable part. So this variable part is dependent on the component variables. So its size is dependent at runtime, dependent on the variables at runtime. So here S of P is the space complexity of an algorithm P. So here space complexity mainly concentrate on S suffix P, that is called as variable part. Next, how to find out the space complexity of these three algorithms. First, we can take this algorithm. So how to find out the space complexity of an algorithm? So S of P is equal to C plus S suffix P. So here C is nothing but space needed for variables. So space needed for variables and space needed for constants. So here there are no constants are there. So here space needed for the variables. So here C is equal to space needed for variables. Space needed for the variables. So here variable S require one word, variable I require one word, variable N require one word. So how many number of variables are there? N is one variable, S is one variable, loop variable is I. So variable S occupies one word, variable I occupies one word, variable N occupies one word. So that is equal to total, so 3 words. Okay. So here variable space. So variable space dependent on the component variable whose size is dependent on the particular problem instance. Here the component variable is A. Okay. So S suffix P is equal to array A with n values, each value occupy one word, so total n words, so therefore C is equal to 3 plus n. So therefore S of P is equal to, not is equal to, so greater than or equal to, so 3 plus n. So here sometimes it may require some auxiliary memory, or sometimes it may require some reference memory. So at that time we are using greater than or equal to. So S of P is nothing but space complexity of an algorithm P is always greater than or equal to 3 plus n. So here 3 is space needed for variable s, space needed for variable I, space needed for variable n. Each occupies one word, so total 3 words. Plus, so component variable s is array A with n values. Each value occupies one word, so there are n words are there. So s suffix p is equal to n. So therefore 3 plus n. The time space complexity is s of p greater than or equal to, so 3 plus n. Why we are using greater than or equal to? So to execute this program, sometimes we may require auxiliary memory. So at that time, so we are using greater than or equal to. S of p greater than or equal to 3 plus n. Next, go to this one. So time complexity of an algorithm P is equal to C plus S suffix P. So here there is no variable part is there. So therefore C plus 0. So here there are no loops are there. So no switch cases are there. No if else statement is there. So at that time S suffix P is equal to 0. So here C is equal to, so space needed for variables. So A comma B comma C. So each occupy one word. Each occupy one word. So therefore S of P is equal to, so 3 plus 0, so that is equal to 3 words. Next, go to this algorithm. So this is a recursive algorithm. So the recursive algorithm can be implemented with a stack. So here the return address is always stored on the top of the stack. So here the return address occupy one word. Return address occupy one word. So here this is an array. So this array contains the base address. So this base address is pointed by the pointer variable. So here pointer to an array. Pointer to an array A occupies one word. Next, variable n occupy one word. Variable n occupy one word. So there are total 3 words are there. Next, where the recursion fails. So here the recursion can be represented by using a tree. That tree is called as recursive tree. So where the recursion is failed at n plus 1th time. So therefore depth of the recursion is equal to n plus 1. So therefore the time complexity S of P greater than or equal to 3 into n plus 1 time. So how many times this recursion can be called? That is n plus 1th time it may be failed. So n plus 1 times it can be called. So that is 3n plus 1. So how many number of words we are required? So that is return address occupy one word, pointer to an array A occupy one word, variable n occupy one word. So there are 3 words are there. So space complexity of an algorithm P greater than or equal to 3 into n plus 1. So in this way we have to find out the space complexity of an algorithm. Next, we go for time complexity.